Hello, so continuing on this weekly contest 317, the last problem, which is a hard problem, a height of binary tree after subtree removal queries. So let's take a look here. So we have a binary tree with n nodes, and each node is assigned a value, a unique value from 1 to n, and we get also an array of queries of size m, so a different size. And what we want to do is do m queries, independent queries. So basically each time we start from the original tree and apply that query. And in that query, what should we do with that query? Basically we want to remove the subtree that is rooted at the node that has a value that is the same as queries at position I, right? And it's guaranteed that that element is not the root itself. So we don't need to remove the entire tree. And what we want is return an answer array of size m. So for each query, we want to return the height of the tree after performing that query. And the query is removing the subtree that has that node value as the root. So yeah, they say the queries are independent, which means each time we need to start from the initial tree state. And the height of the tree, what they mean by that is the number of edges of the longest path from the root to some node, right? So for example here, let's take a look at this tree that is represented by this root. Queries, there is just 4. So we want to remove the subtree that has the root 4. So root 4 is here. So we want to remove this subtree here, right? So we remove this. So we end up with just 1 and 3, and the length here is 2. So we return 2. Let's take a look at the second example. So we have first query 3. So we start with that. So 3, we just remove this. The longest path is this one here, right? This one. And the length is 1, 2, 3. So the length is the number of edges. So we put 3 here, okay? And then we start again from a new tree, the same initial tree. So value 2. So we want to remove this subtree here, right? And so we are left with 1, 2, that's the longest. So we put 2 here. And then we go to the second example with 4. So we want to remove just the subtree that has value 4, so that has root 4. So we'll remove that one. And the length is still 3, right? The longest path. So we put 3 here. And then lastly, 8. So for 8, we remove all the subtree here, right? And we end up with just the longest one is 2. So we put 2 here, right? So that's roughly the idea. Okay, so that's how the problem worked. Now, how do we solve it? We definitely can do a DFS on each time, right? Each time remove and then calculate the height, right? But that would be expensive because we will need to do for each query, so O of m, right? And the query is up to n, so it's up to 10 to the power of 5. And then we'll need to do a DFS to calculate the large height after removing, right? So that would be also 10 to the power of 5. So it would be 10 to the power of 10, so that's too expensive. So let's take a look at this example here, the second example. How can we accomplish this? I think first we need to think about what is the height that we are looking for here. So for, let's say, from the perspective of a child, right? From the perspective of a root, right? The length is just all the edges, descendant edges, right? But from the perspective of this one, for example, 2, even let's imagine if you had even more subtree here and another subtree here. From the perspective of 2, what is the overall length that passes by 2? Well, it's the height of the subtree that starts at 2, right? And what is up to 2? What is that? That's just the level or the depth of 2. So this here is the depth of 2. And so the overall path length is height plus depth, right? So that's the overall path. So the overall path is height plus depth, right? Let's remove this subtree. But if it was there, then that would be the height, right? That would be included in the height. Okay, so how can this help us, right? We know that for all elements that are in the same level here, right? Those have the same depth, right? Because they are at the same level, right? So they have the same depth, right? Okay, so if we remove 2, for example, then what is the what becomes the height of the tree? What becomes the largest one? Well, it will, since the sum of the length is height plus depth, and depth is the same, right? It would be the one of these on the same depth that have the highest height subtree, right? I hope that makes sense, right? Because let's say we remove 2 here and 7 maybe had 3 other children, right? Say 3 like this maybe. Yeah, so if we remove 2 here, right, then we need to just look at the elements at the same level, okay? And count which one has the largest height. We don't need to worry about the depth because it's the same. And the one that has the largest height, that's the one we need to return the height of it plus the depth, right? So that's the fundamental idea here. Okay, so that's the first thing. So what does this tell us that we need to compute? Well, we need to definitely track the depth and height because we'll use those. So those are the things we need. So we need let me just make this writing better. So we need the depth map, right? Okay, we need the depth. And this should be basically the node as a key and then the depth as a value. So node value and then depth. Okay. And then we need the heights also to obtain the height, and that would need to be from the node value again to the height. So this would be the key, this would be the value. Okay, and the other thing we needed, so when we get in a query a node, right, we want to be able to tell who are the elements that are in the same level, right? We can call them maybe, we can't call them sibling because siblings are only those that have the same root, but maybe we can call them adjacent or something like that, right? So we need to keep track for each node, we need to get the adjacent to it. Or like maybe level, let's call them level, right? So levels. Okay, so levels would be, the key would be the depth itself and the nodes that are in that level. Okay? Okay, so we know that we need these. Now, the thing becomes, how do we respond to each query? All of this, we are doing all of this to avoid for each query doing a DFS path, a new DFS pass, right? So we can populate these two in one loop, in one DFS, and then we can populate levels in one loop, right? So let me just note that down. So what we'll do is this is in one DFS, and then we'll do this in one loop. I will show how in a minute. Okay, so now once we have these two, how can we get for each query the height, the new height, right? So for each query, how do we do that? Well, the answer becomes easy. When we are doing these levels, what we need to do, we just need to keep track of the two highest height. Why is that? So for example, in this case, let's add our level depth here. So this is 0, here 1, and here 2, and here 3, and here 4, here 5. This is just suppose the example has more elements, right? I'm supposing we have even more here. Let's say maybe this is some values, 10, let's say 12 here, 10, maybe 14, 15, something like this, or maybe 11 here, then 13, for example, something like that. So if we have this, then let's say for level 2, what we need to keep track of is just 2 and 7, because we will, for each query, we'll remove only one element. If we remove 2, then the highest height is the one at 7, and so we need to grab the height of that in the depth. If we remove 7, then the highest height is 2, and so we'll grab the height of 2. If we remove 3, then the highest height is 7, so we'll grab the height of 7. If we remove 1, then the highest height is the one of 7, and we remove that, right? So we only need to keep track of 2 highest height from a level. So for each level, this is an important piece as well. So for each level, keep only the 2 nodes of highest height. This is because we'll remove only one at a time, and so at most it would be one of the ones with the highest height, and we can take the next one, right? Okay, so when we do this, how do we solve for the query? So we would just do inquiries. We will check if the number of elements in that level, so levels at, so first we need to get the depth for this node, and to get that we already have the depths map, so we get that, and so we check the levels in that, at that depth, how many nodes are there. If there is only one, that means there is only one element. Let's say, for example, we want to remove 6. 6 is not a good example. Let's say, for example, we want to remove this 13 here. Let's say Q is equal to 13. So the length, so what we need, so if we remove this one, then what we need is just the depth of one before it, right? So just the depth, there is no height because we removed this one. And so if it's equal to 1, then in our result, we want to just add d minus 1, because that's the only one we remove. Just depth minus 1. Now if otherwise we are in one case, either the largest height is the one for the query we want to remove. In that case, we want to take the next one, or it's not even one of them. Let's say in the case of 3, in that case we want to take the highest one, which is the height of 7, right? And so either the levels at position at D, right? The value there, the node, let's say, so the first one, either the first one in the node, let's say we put the node in position 1. If that's equal to query, that means the highest, we are actually removing the highest one. So that can happen if Q is equal to 7, right? If Q is equal to 7, that means we want to actually remove this subtree here for 7. And so we just need to grab the next largest height, which is 2, which would be, since we add 2 levels only, the 2 largest one, it would be the one in position 1. So in this case, we want to add to res levels at position D, position 1, because the next largest, because we are removing the first largest, and we want to get the height, so 0 plus the depth, right? So this would be the height, right? Remember, we are saying we want depth plus height. Sorry, I went too far. We want height plus depth here, right? Okay. So, okay, so now this means that we need to put in levels, we need to put both the node and the height, right? So here, levels has, each one has a pair of the height that we already calculated here, so we can obtain it by just doing height's node val, and then the node val, okay? Now, one thing to note is we want the largest one. We want to select the largest one, so we want to put this minus so that if we sort, this would be the first one, right? Okay. We could also sort in reverse and leave it positive if we want. And so here, when we are adding it, we want to put -1 in front so that we get the proper height. Now, otherwise, that means Q is not actually the first largest height. And so in that case, let's just return the first largest height. So in that case, Q, for example, is either 3. So then we want to just return the height for 7, right? Because that's the largest one at this level. Or, for example, it's 1. In that case, the same thing. Or even if it's 2, because that's not the largest one, the largest height is 7, then we just return 7. So in that case, we just want to add the height for 7, which is levels at D, 0, because we want the first largest. And to get the height is at position 0. We do -1 because we added -1 at the height initially. And then we add the depth because we are doing depth plus height. That's the initial, what we said initially here. It needs to be depth plus height. Okay? So that would be the final thing to get it for all of them. And now notice what we did. We set up all our maps that we need first using DFS in one DFS, and then for the for loop for the query, we just used that data, and we did for each query, we did O of 1 here. This is O of 1. The solution that we are doing here is O of 1, right? And so that makes it so that the first DFS is O of the number of vertices plus edges, so that's O of n. And then we do for the levels, we also only traverse depth once, so, and then we do a loop, so maybe it's O of n like n depth. And then here we do only O of m, right? So we separate it kind of, we prepare with the data that we need, and then we do the O of m query solution here for that. So how do we fill depth and height? Here, let's do that. So we need a function for DFS, and if not node, which means we are in a leaf node, we want to return some base case. We'll see later what that should be. But each time we just want to say that the depth of this node, so we take the value because the values are unique, is equal to D. And each time we go down to left and right, the depth increases by 1, right? So we know that we want to go left. So that would be on D plus 1. And we want to go right. So that would be on node dot right, on depth plus 1. So this would be enough for the depth, but we also want to compute the height. So the height is just the max of the height of the left and the right subtree, right? So this would be the max between these two. But each time we go down, we increase the height by 1. So this would need to be plus 1, right? So let's call this H, right? And then when we are done, we want to fill the height for this current node. When we are done going through all the children of that node, we want to fill the height of that node to be equal to H, right? And we want to return the height upstream, right? Because that's what we use here to assign. So we want to return the height to the parent. Okay, so basically you can think of it in the tree here as each child goes down and tells 8, for example, calculate the height for your subtree, and so it will return 2, and then 5, it just adds its 1 for this edge and assign it to itself. Okay, depth is straightforward because we just pass it and we assign it. There is only one problem here because the height counts the edges, not the nodes. Right, when you get to the final one, right, we shouldn't count this one, because if we count it, then instead of, for example, for 5 to 4, instead of being 3, it would be 4, right? So to just cancel that one out, we want to return -1 in the base case here, just to cancel, because we want to count the edges, but with this +1 we are counting the nodes. So to cancel that last one, we do -1 here for the base case. So that's the idea. Okay, so now we know how do we compute depth and height. Now the problem becomes, how do we compute for the levels? Well, that should be an easy map. We can just do a map on the depth, right? And then for each one, levels depth, we want to append the height and the node value. We have the height and we have the node value, and we want to append But since we want to keep each level have only 2, if we have more than 2, we want to pop, right? We want to remove the smallest one, right? And to do that, we can just remove from the end because we have -1, and that will remove the smallest one. So that will keep only the 2 highest ones. We'll see this in the code later. So we'll just make sure we do this here when we are calculating the levels. But otherwise, it's straightforward using height and depth. Yeah, so that's pretty much the idea. We'll do 3 parts. The first part is populating depth and height. The second part is populating levels. And then the last part is just doing the queries. Yeah, so let's implement this. Okay, so let's implement this solution. So first we need depth, which is a collection of lists. And then we need height, which is a collection from node value to int, right? So that's what we said here, from node value to int. What we said here. So this would be int then, so that it initializes to 0. And first we'll do the first DFS, right? And that DFS will start from the root, and we will start with depth 0. This would be what we implemented here. So we can just copy that out, copy the exact thing that we implemented. Remember, this is height, so just let me replace this so that it's accurate. So this is the exact logic we implemented here, right? So each time we go down, the depth increases by 1, and then the height is just the maximum between the 2 children, the maximum height of the subtree for each child, plus 1 because this is the parent, right? And then we assign the node value, assign the height in the height map, and we assign the depth in the depth map, right? And we do it at the end because, remember, the height is from the node down, the depth is from the node up. So that's why the depth is assigned first and then the height is assigned later. And -1 here to cancel out the last one because we are counting the edges for the height, right? So the function basically returns height. So DFS here returns height for node, okay? So now we did the first part. The second part now is computing levels. This levels map. So let's define our levels map first. So it's also a dictionary and it needs to be on a list, right? Because it's the list of all the nodes at a particular level, right? So this would be the list of all nodes, let's say, for example, in this level. So 2, 1, 3, 7. So to do these, well, we'll go through all the depths element. So we'll get the node value because that's what we add here. So node val, and then we'll get the depth, which is, let's call it D, in depths items, right? And for each one of them, the levels is just those that have the same depth. So just make the key be depth. And what we want to add, a couple of things. We said we want the height negative so that we can get the largest one. And then we want the node value, right? So that's what we said here. So that's what we want to going to add. To get the height, well, the height is just in heights node val, right? So that's what we are going to add here, a pair of that. And then the node value, that's what we have here. Okay, this is to compare it to Q that we do later in the query here. Okay. Okay, so once we add it, we want to sort because we want to only keep the 2 largest height. That's why you see we done here minus so that we can do levels D and sort each time. And then here we want to keep only the 2 largest height. So we want to remove those that are bigger. So if ever levels length is bigger than 2, so levels for this depth is ever bigger than 2, we want to pop the last one. And since we are sorting, right, the last one would be the smallest because of minus. So it would be, let's say if we have -7, -6, -5, -4, okay, more than 2, so just like this, right? So what will pop do? Pop will remove -5. -5, even though it's the larger in terms of negative value, is actually the smallest in terms of positive height, right? And so we want to remove this one. And so that's what we do with pop, is remove the last element. Okay? And so we pop that, And now we can just do what we did here, because now our levels, we know that they are populated, and we know we have only the two largest heights because of this sort and this pop. Okay, so now we do the last step. So we did the first one with the DFC, with DFS, and we did the last one, the second one, to populate levels. Now we just do what we did here for queries. So that would okay, so now we do for the queries what we did in the overview right here. Okay, so basically if it's 1, we are in the 3 or 1k or 1 or 2 case, right? Sorry, we are in the we are in a case like this where, for example, the 13 case here, right? The levels contain only 1 element. In that case, we just remove it and we return the depth for the one before. So that's why we do d-1. That's the depth of one before, because that's all of this here, which is all what we need. Then we check if the highest one is actually the one we want to remove. If it is, we take the second highest, which is, if it is, we take the second highest, which is what we are doing here with this one. Otherwise, we are removing what we are removing is not the first highest, so we just return the first highest height, right? And then we return a result at the end. And so that's pretty much it here. Yeah, so a little bit complicated, but once you do the processing and get the data you need, this step becomes easier. So let's run this, make sure it passes. Looks like there is a problem here because, yeah, we already have node value, so we don't need to do node.val. And this is, by the way, possible because the node values are unique. And let's submit. And this passes test cases. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.